Okay, so let's start talking about performance, because the whole reason we built caches is to have lower power and higher performance. And let's go back to the iron law. So what is a cache trying to do? Well, what a cache is trying to do is if you look at that iron law of processor performance, when you do a load or a store, we're trying to decrease the clocks per instruction to process that load or the store. So if you have to go all the way out to main memory in a cache miss, we'll say, or if you don't have a cache, it's going to take a long time. But if you shrink the cost per instruction for a load and store, everything gets faster. So you can actually go faster here. So as a sort of showing here, we have some loop that does it load, some adds, and here it takes a cache miss. If we can somehow do things to the cache which reduce the probability of a cache miss, we can shrink the amount of time it takes to do that, and the whole program will run faster. So reducing our number of cache misses is good. Using our cache to actually keep the data local. And also, sort of as you can see here in this diagram, this first load here hits in the cache. So it doesn't have to go out to main memory. So it just hits, and if it's a properly pipelined cache, it'll just return the data on that load. Just wanted to introduce, sort of in this diagram, two things. Processor to cache and coming back, that's a hit in the cache. Miss takes longer, it just takes more cycles. Okay, so this is an important slide because it introduces some important ways to think about caches. So we want to categorize the types of misses we have to cache. So this is figuring out why we will have these different heuristics inside of caches based on the different policies or the different ways that you could actually have a cache miss. And a lot of times people call this the 3 C's of caches. Okay, the first C, a compulsory cache miss. So what that means is that it's the first reference to a block, and you're going to take that cache miss even if you have an infinite sized cache. It's just you can't get things into the cache unless you go to try to access them the first time ever. So that's what a compulsory cache miss is that first reference. You can try real hard. You can think about having a prefetcher actually to try to reduce the amount of compulsory cache misses. You can think really hard and say, oh, I think I'm going to access this data sometime in the future. I should go get it. And then when you go to actually go access it, you won't take a cache miss. So that's a possibility. Okay, the second C that contributes to our performance of caches is the capacity of the cache. So traditionally, a larger cache will be able to fit more data. Well, that's always true. But traditionally, a larger cache, you will have a lower miss rate if you have a larger cache. So let's think about that. This is an important question here. Will a larger cache always have a lower cache miss rate than a smaller cache? If in a loop, let's think about what kicks data out. If you have a cache that is, let's say, 8 lines, and you have a cache that is 16 lines. By definition, the addresses that would alias in the bigger cache are going to alias in the smaller cache also if you go, let's say, from a 16-entry cache to a 8-entry cache. So it's actually, if you're going up by factors of 2, at least, your cache miss rate is always going to be better with a larger cache. Or the cache miss rate is going to be lower with a larger cache. The one place it could actually come up is if you try to change the hashing function. So if you have a cache that is, let's say, 2/3 the size, you have a cache that is, let's say, 8 entries, and you have a cache that is 12 entries. So there, the hashing locations are going to be different. You can actually think about having different patterns there. But it's likely that the larger cache will still do better than. So large is good. That's assuming like sort of direct mapped cache. You could, depending on your L or U strategy, probably, or your replacement policy. There's probably some other caveats there I'd have to think a little bit harder about. OK, so finally, what's the last thing that can cause a cache conflict to occur or a cache miss to occur is conflict in the cache. So this means that we don't have a high enough associativity in two different pieces of data or two different blocks alias to the same location, and they're fighting for that location. So there's conflict there. And one of the pieces of data gets kicked out before you have the time to go read it back in. So you have a load and then another load, but in the middle time, you have a load to a different address, which happens to alias to that same location in the cache. The hash function points it to the same location, and they're going to fight for that resource. So that's a conflict. OK, so let's put some data behind this and look at some ways to make caches go faster. OK, so let's look at what we're plotting here on this graph. On the x-axis, we have different sized caches. 16 kilobytes, 32 kilobytes, 64. So we go up by factors of 2 all the way up to 1 megabyte. On the y-axis here, we have access time. So how long it takes to access the cache. So if we go back to this average memory latency equation, we take the miss rate times the miss penalty plus the hit time, how long it takes to actually go sort of look stuff up and find something in our cache in the first place. Well, if we can reduce the hit time, that's good. So if we take a cache which, let's say, takes, I don't know, 2 nanoseconds to access, and on a 1 gigahertz machine, that would be 2 clock cycles, and we can somehow replace it with a cache which takes half a nanosecond to access, that's good. That means we can actually fit that in 1 clock cycle on our 1 gigahertz machine. In fact, we can probably go all the way up to sort of 1 nanosecond on a 1 gigahertz machine before we spill over into the next clock cycle. So you can sort of think about that. So first thing is actually small and simple caches could be good. Everyone thinks capacity, 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 but in your sort of processor core, if you can reduce the hit time, that's a good thing. So just to give you some idea here, as you scale back, you can have to the smaller caches, the time it takes to access the cache goes down. So the next thing you do is we can try to reduce the miss rate. And there's a couple different ways to do that. These are just sort of some basic optimizations. In the cache lectures later in class, we're going to go through a lot more optimizations for caches. But one thing you can do is think about looking at the block size. So the examples I've been giving, we're talking about 64 byte block size. But you could think about having either a smaller block size or a larger block size. And in fact, this happens. This graph here, 64 looks like sort of the lowest miss rate is a good spot. But this is really dependent on your applications space. So if you have applications which just sort of stream through memory, you probably want a bigger block size. If you have more random patterns, you're not getting any reuse, it might make sense to even have a smaller block size. So this data is from your textbook, actually. This is plotting specint rates with different cache sizes. So each of these lines here is a different sized cache. So you can see 4 kilobyte cache, 16 kilobyte cache, 64 kilobyte cache, and 256 kilobyte caches. And you can plot those two things against each other and see where the sort of sweet spot in this curve is. And we're trying to minimize the miss rate, so how often we actually take that cache miss. OK, so there's some positive things here about having different, having larger cache sizes. Let's talk about that. So if we have larger block sizes. If we have a larger block size, we need less tag overhead. So we talked about that already in the tag lookup slide. You can if you have longer block sizes, you can think about having more burst transfers from your DRAM. So in DRAM, typically they like to give you like sort of large chunks of data at a time and not little chunks of data, because there's a overhead cost in firing up the DRAM, and there's what's called the column address strobe and the row address strobe, or RAS or CAS time. And you have to do that for memory at every memory access. So if you can sort of pull in larger chunks of memory at a time, you only have to do that once for the large amount of data you bring in. So that pushes you to actually want to have larger block sizes. And you could even think about having similar ideas here for sort of on-chip buses. If you have larger block sizes, you'd probably be using that on-chip bus more effectively, because there's some overheads and some turnarounds usually for arbitrations for buses. OK, so on the right side here, we have the downsides of larger block sizes. If you have a larger block size, you might be pulling in data you're not using. So if I have a 256-byte block, cache block versus 64-byte block, we're going to be pulling in 4 times as much data. And if we're only trying to access, let's say, 1 byte in that data, we just wasted a lot of main memory bandwidth to go pull that 1 byte in. So we have to be cognizant of that. And that's why this curve is not increasing one direction or the other direction. Because when I sort of first took a computer architecture class, I thought, oh, as you increase the block size, shouldn't performance go up? Or shouldn't the cache miss rate go down on this graph? And it's not true, because you start to waste bandwidth at some point. Also, if you have larger block size, by definition, you have fewer blocks. So if we have, let's say, 256-byte blocks versus 64-byte blocks, by definition, this is sort of four times fewer blocks in the cache. It's the same amount of data. So if you have a 4 kilobyte cache, we're going to have the same amount. It's the same amount of data. It's still a 4 kilobyte cache, but there's less blocks in that cache, so you're not going to be able to have as much random data in your cache at one time. So this is one technique to reduce miss rate. Another way, in a perfect world, this fights off against small and simple caches, is you can just build big caches. If you build big caches, this means that when you go to access the data, there's a very high probability that the data is close to you. That sounds good. So here we actually have miss rate plotted against cache size. And of course, there's sort of different types of caches here. And let's see, there's one thing I wanted to point out here. This empirical rule of thumb. If you double your cache size, your miss rate usually drops by √2. Sometimes people call this the square root rule. How do we derive this? Well, sorry to break it to you guys. As it says here, it is an empirical rule of thumb. It is just a rule of thumb. Obviously, if this was perfectly true, this line would be nicely curved versus having some bumps in it. But this actually surprisingly works out pretty well as a rule of thumb. So and it doesn't really work very well for very small caches. So typically, sort of right in here, it doesn't work well. Possibly sometimes for very large things, it doesn't work well. And for high associativity, this rule of thumb starts to break down also. But it's a good rule of thumb to think about. OK, so how else do we reduce the miss rate? Well, same graph, but this is also from Hennessy and Patterson in your book. You can increase the associativity. So you can take a 4-way cache and turn it into an 8-way cache. Now, there's some hardware cost associated with that, and there's also clock cycle cost, typically. So let's look at the rule of thumb here. And the rule of thumb basically says a direct mapped cache of size n has about the same miss rate as a 2-way set associative cache of size n over 2. And this that sounds crazy good. How is that possible? It means we should always go at least 2-way set associative caches. But let's look at this graph and see if this actually works. So we're going to look at a point Let's look at a 16 kilobyte cache that is direct mapped and compare it against a 32 kilobyte cache that is, or excuse me, a 16 kilobyte cache that is two-way set associative versus a 32 kilobyte cache that is lower associative. And kind of what you're trying to see here is if this point here is equal to that point. Well, it's not, but it's actually not a horrible approximation. We're sort of saying if we have a 16 kilobyte cache with a higher associativity, our miss rate goes down, right? So it's going to be somewhere in here versus a 32 kilobyte cache, which is direct map, which is this point here. OK, well, that doesn't hold there. Let's go look for another point here. Let's say 32 kilobyte two-way set associative cache, which is that point there, versus a 64 kilobyte cache that is direct mapped. Well, that's almost on a straight line with each other, so it's almost exactly equal. And this is just an empirical rule of thumb that people sort of figured out, that as you double your associativity, you actually have you can almost half your cache size and still have the same miss rate. And likewise, as I said, this is just empirical. There is no reason why this has to be. And it's really dependent on your sort of data access patterns. But I found that pretty interesting. OK, so what's the problem with building a two-way set associative cache always? Why do we not do that? So the area for the data store shouldn't actually change very much. But what does change is your tag store. The tag data, you're going to need, for the higher associative one, you're going to need more tag check logic at least. Because you have to check, let's say, two tags in parallel.